Having looked at the different variables, we can now look at the question of how do we model risk, and this is the focus for this module. Overall, what we're looking at is to test the profitability measures that come from our model as a result of changes in the variables. There are a set of different ways that this has been done over time, and we need to be aware of the benefits and shortcomings of these different methods. The earliest approaches to modelling risk was done by a method known as sensitivity analysis, and while simple sensitivity analysis is no longer recommended because of its simplicity, that general term stays with us as the general name for the activity involved in modelling uncertainty in the variables. However, we'll also be looking at other methods, and in particular spider diagrams, Monte Carlo analysis, multi-dimensional analysis, and scenario analysis. While these are common methods, they are by no means the only ones available, but they do represent the most common ones and the most approachable. Sensitivity analysis is the original form of risk analysis for discounted cash flow analysis, and in fact it goes back to when the early discounted cash flow models were done by hand-held slide rules, even before the days of battery-operated calculators. In that situation, to calculate all of the mathematics for a DCF took a considerable amount of time, and so to rerun the model for many different possibilities was simply impractical. And so the habit developed of analysing the key variables one at a time for 3 values. The most likely value was the forecast value, but then either side of this most likely value, analysts considered the most optimistic possibility for the variable, in other words its movement in a realistic direction that would give a better investment result, and also in a pessimistic direction, which was the adverse change in the value of the variable about as far as the analyst thought it was likely for it to possibly go. And this 3-world scenario became commonly accepted as the norm for analysis of the uncertainty in the variables. We can do this very easily in an Excel spreadsheet by simply changing the values of variables one at a time and recording what value the NPV returns. And you can see this in the inset. There are a number of problems with sensitivity analysis. The first is that the estimation of the forecast value is fairly difficult. Some people would say extremely difficult. But then to estimate where realistically the value might get to in either an optimistic or a pessimistic case and say these are the limits is even more difficult than the forecast itself. And so working out the limits for the optimistic and the pessimistic are themselves quite challenging. There is another problem related to this which is a little subtle, and that is that if, say in the example where we have estimates of the property growth of 1, 3 and 6% being the pessimistic, most likely and optimistic, it really suggests that we're quite confident, in fact we're somehow sure, that the world is going to end up in one of these 3 cases, and certainly we are implying that property growth will never be less than 1% or greater than 6%. However, this is plainly absurd. And so by specifying the extremes between the optimistic and pessimistic values, we're implicitly asserting something that we really don't know, the knowledge of the exact limits of what variation is possible in the variables. This is known as the 3-world problem. The second problem with the traditional sensitivity analysis is that it ignores probabilities of future outcomes. How likely is the most optimistic, 6% in this case? Is it more or less likely than the pessimistic option of 1%? And how do they relate to the most likely? We don't know. Sensitivity analysis is also done one variable at a time. And while we may be able to work through each of the variables in our DCF and allocate optimistic, pessimistic values to them, we have never actually looked at what happens when more than one of them move together. This is known as the covariate effects. What happens, for instance, if the interest rate and the discount rate both move in a pessimistic direction, or for that matter, in an optimistic direction? And so these questions of covariance are completely ignored from sensitivity analysis, and this turns out to be one of its major problems, because it gives us a confidence of where the limits of outcome are going to be for the project, which are in fact considerably more conservative, both in a positive and a negative direction. The choice of the optimistic and pessimistic limits tends to be done by experience or feel. When we talk about experience, we need to be rather cautious. Experience somehow suggests a special, even scientific insight. But in fact, experience simply means that we're relying on what we have seen, say in our time in the industry, or perhaps extended by what we have heard and learnt from the experience of others. If we don't have anything more than simply our limited time frame of experience, then our estimates are eventually only subjective. In other words, they're only guesses. It's hard to say that we've got something more than a guess if our data is simply guesswork. A development of the traditional sensitivity analysis is to produce indications of the effect on the output variables, the net present value or the IRR, on the basis of continuous trend in the changes to the target variables. And this can be seen in this slide with the investigation of rent in the example of the DCF model we've been building over the last couple of weeks. Here we're investigating the changes in net present value for changes in rent between $23,000 and $30,500 per year. Now you'll notice that the expected level is somewhere more or less in the middle in there. But rather than selecting optimistic and pessimistic extremes, we have avoided that by simply investigating the entire spectrum of possibilities. This table is easily generated using the table function in Excel, and we've already learnt how to do that in the FinTuit exercises. Likewise, on the right of the slide, we can see the table expressed as a graph. It turns out that the graph is a superior way to present this information to a client or to your organisation. And the reason for this is that a graph is very effective at communicating the overall trend and the rate of change in the output variable, the dependent variable, the net present value in this case, for changes in rent. And this means that the client themselves are able to put their finger on where they think rents are going to go and then read off the net present value result. Another advantage of this is that by using a graphical presentation, the apparent extreme precision that we find in the table on the left of the slide is avoided. If we look down the table, we've got numbers like $6,792 of net present value, ranging up to $27,671. Plainly, these precise values are really never going to be expected to happen. We don't pretend to know net present value down to the nearest dollar. We probably only know it to the nearest $5,000 or $10,000. This suits a graphical presentation rather than the table presentation, because the graph is only able to be read at the level of precision which is comparable to probably the level of precision of the model itself. As well as the single variable sensitivity analysis that we see in the top chart, we can also use the Excel table function to analyse pairs of variables moving together. And this is done in the chart at the lower right hand side of the slide, which shows the behaviour of net present value versus rent and property growth. There are a number of different ways of presenting this three-dimensional data. Here we're using a series of lines on a two-dimensional chart. There are a variety of three-dimensional chart forms available through Excel, and it's often useful to become familiar with them. These include three-dimensional column graphs and surface charts, and these can be very powerful ways of communicating the results. Again, if we look at the traces on these charts, we can select a particular choice of property growth, and that gives us one of the lines on the chart, and from that and a selection of rental, we're able to see what the NPV is. The advantage of the three-dimensional charts, that is two independent variables and one dependent variable, is that we're able to look at the interaction between variables. This is extremely important because often the variables behave in different ways depending on the settings of other values in the model. Here we can see that each one of the property growth traces gives what appears to be a parallel line running up as rents change. Sometimes the gradient of these lines change, and you even have the lines intersecting and overlapping. And so you end up with some very interesting results. It's important for analysts, once you've built your discounted cash flow model, to build a large number of tables, both single values such as the one on the left of the slide, but more importantly the two value tables, the row and column values or variable tables that we have done in Fintude to produce the kind of graphs that you see on the lower right hand side. The more of these you produce, the stronger your understanding of the interaction of the variables will be in property investment. And while we're using the DCF tool to do the analysis, the insights you get from this exploration will serve you well in many other aspects of your professional lives. While the production of tables and charts is something which is very straightforward to do on an Excel spreadsheet and is highly recommended, an earlier approach to dealing with some of the problems with sensitivity analysis found its way into a presentation known as spider diagrams. Spider diagrams are in fact a form of graphical presentation of traditional sensitivity analyses of a number of variables, all presented on a single chart. And so it's a graphic presentation of sensitivity analysis for many variables. Each variable is examined for an increase and decrease in value, but the increase and decrease is worked out as a percentage, either growth or reduction. And in that way, regardless of whether the variable is itself a percentage or a dollar figure or whatever, the fact that the optimistic and pessimistic ends of the possibilities will be in a number of different types of units. By reducing them all to a percentage increase or decrease, all of those percentage increase and decreases are able to be expressed on a single x-axis. And so all of the outcomes can be plotted onto a single chart. On this chart we see a selection of plots for most of the variables in the model that we've been examining. You can see the table on the left includes most of the variables in the DCF model that we've been building over the last couple of weeks. So you can see it ranges from tax rate down to rates and taxes. And we have the increase and decrease that's expected in the upper and lower possibilities of these various variables. And so in the case of tax rate, we consider that taxes may increase by perhaps up to 20%, or perhaps they might reduce by 40%. And this gives us the optimistic and pessimistic bounds. And we do a similar estimate of the upper and lower bounds expressed as percentage changes from the most likely for all of the other variables as well. These have all been calculated for the DCF model in our construction exercise, and they've simply been plotted in the chart on the right in terms of the percentage change from most likely And you can see here the range is roughly from minus 300% up to plus 200%. In other words, an increase of 1% becoming 3%. The NPV results for each one of these possibilities is shown on the vertical axis. And so while we can see a cluster of values in the area of about $12,000 to $18,000 NPV, there are also outliers that range considerably higher, up to about $80,000 and down to about minus $30,000. Before we leave this chart, just be wary that each one of those dots represents a different variable. You can also see that in some cases you can have a very large variance in the independent variable without having a great deal of impact on the at present value. By the way, the value of the NPV for the most likely is about $12,000. So it sort of sits fairly close to that cluster of dots immediately under the $20,000 line. But you'll notice that most of the results are somewhere in the vicinity of net present values between $0 and $20,000. When spider diagrams are used, they tend to provide this kind of confidence. We can see on one graph the distribution of possible results of net present value for all of the different variables. And so we can see this cluster, which tends to give us an indication of what kind of results the model will produce, or rather the project will produce, under different scenarios. The graphical presentation of the spider diagram can be very impressive, and it can lead to a nice feeling of confidence that a good understanding of the possibilities for the project have been investigated. And so for this reason it is very nice for a psychological feeling of understanding and confidence. However, there are a number of problems with the construction of spider diagrams that we need to be aware of. The first thing is that the spider diagram itself suffers from the basic problems that we find with the traditional three-value sensitivity analysis. And that is, first of all, that the values are all adopted by feel. We really don't know whether the values for tax or rent or what have you do have the limits that we've set. We really have no scientific way of saying that we know for sure that is the limit which is going to be encountered sometime in the future. The values are adopted by feel. Closely related to this is the three possible worlds for each variable. Again, we have this feeling that we won't be able to get outside of these three values. Somehow they put a limit on where we think the project will run. But in fact, all we're doing is suggesting where we feel the limits will be, not necessarily where they are. Likewise, although the spider diagram does do a nice job of bringing all the variables onto one graphic presentation, it totally ignores the covariate effects. What happens, for instance, if more than one variable move adversely? Again, the same problem that we had with the sensitivity analysis, because although we may have this cluster of dots on our chart, that is only if all of the other variables remain totally as we predicted. However, if more than one of them move, say, either adversely or positively for us, the resultant impact on net present value can be quite alarmingly high or low. It basically blows it out of the water. Because of this, the spider diagram is something that you need to be very, very cautious with, because it can easily be very misleading. Not because it intends to, but simply because it conveys the impression that all of the variables have been analysed, and therefore we have an understanding of the limits of the profitability of the project. Whereas in fact, it's far more likely that if the world does go badly for us, many of the variables will look poorly. And in that case, the result will be well outside of the envelope of possibilities that seem to be suggested by the cluster of plots on the chart. For this reason, I would recommend that spider diagrams be used very, very cautiously, and wherever they are, some sort of a notation to point out to the reader that the covariate effects especially have been ignored, should be made very, very prominently. You can see with a number of these forms of analysis, the major problem is that we're not able to analyse more than one or two variables at a time. But the world is a far more complex place. If interest rates go up, discount rates probably will go up also. Economists believe that inflation would probably go down in that case, and so perhaps may property growth, although history seems to tell a far more complex story. And certainly there are other correlations between likely rentals and levels of prevailing interest rates, and so on, to the extent that the number of interactions between the variables is very, very complex. All this suggests that analysing the variables one at a time is in fact really quite naive and perhaps even misleading. The best we can do, as we've suggested, is analyse them two at a time, and with a bit of care you can take this a little bit further if you're thoughtful. Excel has an option built into it which does enable us to do something far more powerful, and this is known as scenario analysis. In scenario analysis, we produce forecasts which are complete forecasts of all of the variables. And the basis of scenario analysis is that we consider different possible future worlds, perhaps hanging on particular future possibilities. And we look at the settings for the values of the entire suite of variables that are used in the discounted cash flow model for that particular scenario. And then we put that package of values into the model and see what the result is. In this way, we are able to analyse complete sets of values, complete possible future worlds, in a sense. And we're able to look at not simply an optimistic or a pessimistic view for this value or this variable or the other, but rather an optimistic world where the economy is booming, or a pessimistic world where it falls apart, or perhaps a world where there's political mayhem or some new technological innovation or a improvement in transport infrastructure or manufacturing efficiency. There are a number of different scenarios that we can consider in this vein, and for each one there will be a complete set of values for the various parameters. This is important because when we build the scenarios, they need to be somehow a realistic set, a compatible set, not simply an optimistic set where we set all of the variables in a way which will either improve the investment performance or conversely make it worse, because often these uniformly optimistic or uniformly pessimistic sets of variables are quite unrealistic. They can't happen in practice. The advantage of the scenario analysis is that we can go back to the old categories of optimistic, pessimistic, and most likely, because what we're looking at is an optimistic worldview, which is a complete worldview in optimism or a complete worldview in pessimism. Implicitly, the scenario analysis does include covariate effects, because the selection of the scenario, that complete set of values for the variables, does consider the covariance between them, the likely interaction between them. Scenario analysis has the disadvantage that you are only able to analyse a discrete number of future worlds, and while 3 is a useful minimum, there is no need to stay with that. And in fact, a thoughtful student or a thoughtful analyst can work out considerably more than the optimistic and pessimistic hanging off the most likely. We can look at things like the impact of various sort of changes to the world, whether they're physical or economic. And so it's useful to model several possible likely worlds. And so 3 would be the absolute minimum, 5 would be better, and perhaps more. The important thing about the scenarios is that they're realistic, and this can be achieved by making sure they have a story. And that is, think about a particular future world, maybe dominated by some particular theme or event or economic situation, and then look at what the likely set of parameters would be. What would interest rates and inflation and rents and so on and so on and so on all be? And in this way, the story for each scenario is very important. Students often find that creating these forecast stories is quite challenging. And the reason is that it's one thing to forecast what the future world might be, but when it comes to forecasting a future world, say where the carbon tax has decimated the economy, or where terrorism has had some impact on the way that property is done, or perhaps the change between urban and rural living. These scenarios are all realistic. They all would suggest a particular set of parameters, and it's really the story that makes the individual scenarios likely and believable. What should be avoided is simply taking all of the parameters in the optimistic scenario all in the direction that makes them about as useful as possible for making the property profitable, and then in the pessimistic make all of them so miserable and problematic that they would definitely drive NPV very, very badly. Excel has a very powerful built-in function to do scenarios, and it's worth better students investigating how to operate the scenario analysis tool. While it's beyond the scope for the normal course, I'm sure that there will be students who will be quite interested and capable of mastering this tool. The availability of powerful computing tools has made available a number of analysis tools which have vastly improved our ability to mathematically analyse variation in the variables. However, they are not without their own shortcomings, and so it's important for us to look at some of the methods which are available through the use of powerful computers to the analysis of risk and uncertainty in the variables. The first I want to look at is probability distribution analysis. One of the problems with sensitivity analysis that we have noticed is that we have the three-world problem, the way that we arbitrarily decide on what the pessimistic and optimistic extremes are. We can overcome this by, rather than specifying a discrete limit in the positive and negative direction, but rather conceive of our estimate as a probability distribution, much the same as what we find in statistics. And this way, rather than committing ourselves to a hard and fast number beyond which the variable notionally can't reach, we have instead a normal distribution, or some sort of a bell curve distribution, that simply allocates lower and lower probabilities to values of the variable that are further and further away from our most likely expected value. If all of the independent variables are conceived of as probability distributions, the computation of the net present value doesn't produce a single point, but rather also a probability distribution of net present values. This is satisfying to the statistician, and still the mean result is believed to represent the most likely of the distributions of independent variables. And so this means adding to each variable the other parameters that we normally associate with statistical values. Now, the difficulty with doing this, while conceptually it overcomes one of the considerable problems with sensitivity analysis, it means that not only do we have to forecast the expected value of the variable, but we also have to estimate its statistical parameters. These include the mean, which is the most likely estimated value, but also the variance, the standard deviation, the spread. In addition to expected value and variance, the distribution also needs an indication of skewness, in other words, the lopsidedness of the distribution, and lastly kurtosis, which is a measure of the pointedness of the distribution, if you like. It's not necessary to go into these parameters in detail, sufficient to be aware that if we're going to take the approach of analysis through a probability distribution approach, we need not only forecasts, but we also need estimates of something like at least 3 other parameters for every variable. And so in our case, where our model had about a dozen variables, it means that that dozen variables turns from being about a dozen forecasts to something like 50 forecasts. Very closely related to this difficulty is not only the number of forecasts required, but also the difficulty in actually calibrating these different parameters. It seems that at least at present, there's no scientific way of attributing variance, skewness and kurtosis to these forecasts. It becomes a problem. A related difficulty with probability distribution is the matter of covariant analysis, and that further multiplies the number of parameters that need to be estimated. What we can conclude is that while we have the computer power to be able to change our sensitivity analysis into a probability distribution analysis, the difficulty is that despite our ability to process probability distributions, we simply do not have a practical way of calibrating them. And so our conclusion is that while they're nice in textbooks, they're certainly not scientific at this point in history. Closely related to probability distribution analysis is Monte Carlo analysis. This form of analysis is really a development of scenario analysis. To use Monte Carlo analysis, you need an add-in to Excel or specialized software. Basically, what Monte Carlo analysis does is take your model, in this case a DCF model, and you specify the amount of variance you permit in each one of the variables, set the computer going, and the computer will randomly set values for each of the variables within the limits that you set, and then calculate the net present value of the resulting model. The nice thing about Monte Carlo analysis is that when you set a computer to solve a Monte Carlo analysis problem, the computer can evaluate the model many, many thousands of times. Each iteration of the model represents one randomly selected set of values for each of the variables, evaluated into a net present value, and then statistically collected together. It means that the input values are input as ranges rather than particular numbers, and whereas in sensitivity analysis we were talking in terms of optimistic and pessimistic, we can set values that may be a little further from that. In some cases, Monte Carlo analysis enables the statistical parameters of variance, skewness, kurtosis to be input as well. And so it appears to solve all of the needs of advanced analysis. Monte Carlo analysis is quite popular in some quarters, but it's very, very important to be aware of its downsides. The principal disadvantage with Monte Carlo analysis comes from the fact that each one of the scenarios is randomly generated by the computer. And this means that it's highly likely that many of the random sets of values for the parameters are highly unrealistic. This is simply because they're generated in a completely random way. What this means is that while we may have thousands of runs of the model or iterations of the model, all collected together and presented as a frequency distribution, we don't know which of those runs of the model are in fact realistically possible or not. And so many of them, and perhaps the ones which are most likely to take our eye and influence our thinking, may simply be totally impossible to realise in the real world. And for this reason, while Monte Carlo analysis does give very, very impressive outputs, the likelihood of the Monte Carlo analysis being a realistic appraisal of possible future worlds is very, very low. One development of the Monte Carlo analysis that was intended to overcome this problem was the ability to add covariate estimates. And so the principal disadvantage of the Monte Carlo analysis, and that is that each of the variables is simply randomly estimated or guessed, independent of the others, is overcome. If we say that there's some relationship, say, between interest rates and discount rates, and some other relationship between rents and property growth, and whatever, we can enter into the model a set of covariance parameters which are able to tone down the random allocation of values, which is the principal problem with the Monte Carlo analysis. That sounds good in theory, but the only problem there is that even in a very small model, the number of covariate parameters that is needed becomes extremely high. The number of covariances for a model using n variables is equal to n times n minus 1 divided by 2. This number rises proportional to the square of the number of parameters. By the time this is added to the distribution parameters, the number becomes quite large. For instance, in a model of 30 variables, there are actually 435 covariance parameters, 120 distribution parameters. Hence, to conform the model to a Monte Carlo analysis effectively, there's a total of 555 parameters that have to be estimated and forecast with some kind of accuracy. Estimating the basic 30 variables itself is quite a challenge. Clearly, this is beyond the realms of what is practically scientifically possible. Excluding the purchase price, the very simple model that we have been building in our DCF exercise has 18 variables. Students may like to calculate how many covariate parameters would be needed for even this simple property situation. The result is, regardless of how we use a Monte Carlo analysis, the results are always impressive, but probably meaningless. And given that they're probably meaningless, to take them seriously means to hazard making rather expensive decisions based on something which is deceptively unscientific. This leads us back to where the world currently sits with practical risk analysis. What we've been through in these last few slides is looking at the various tools that are available. What we can conclude is that the most practical approach to the analysis of risk in the variables or uncertainty in the variables is to use the Excel tables, which comes from FinTuit Task 2, and charts, which we found in FinTuit Task 3, on different variables and pairs of variables in our models. While this is not without considerable limitation, at least we can be confident that the results are meaningful, and it does enable us to investigate the interrelationship, at least between pairs of variables. In some cases, if you can look at, say, the rates and be confident of relationship between them, you may be able to look, for instance, at the relationship between real rates moving in unison and inflation, and a few other creative combinations such as that, although these are outside the expectations for the standard level of this course. Once you build your tables, you can check the sensitivity of the model to the various variables and comment. What this means is we can look at individual or pairs of variables, run tables well outside of the limits of optimistic and pessimistic, and so that the client or the manager is able to actually make the judgment call rather than yourself, unless you're specifically called upon to do the forecasting, not simply the analysis. The advantage of being able to take pairs of variables is that you are able to examine cross impacts between pairs of variables and comment. This is very useful. In the case of the assignment, it would be useful for you to run as many two-variable analyses as you can, and then select the ones that you consider to be most interesting and present a selection of them in your assignment. It's important when you present your material to decide what form of communication is going to be most effective. Do you want to communicate using the tables or the charts or both of them? It's also useful to add a brief comment to outline the way that the behavior of the model of the net present value, how that behaves compared to the behavior of the variables that you're looking at. And in doing this, you reveal your understanding of the interaction between the variables in property investment. Make sure you do more exploration than the minimum and include only the most interesting in the reports and assignments. I have mentioned that the requirements of the modelling to make the model sensitive to changes in length of ownership may be beyond some students. I would certainly expect it from the better students. If you do get to investigate the behaviour of the model for different lengths of ownership, it is a very important and interesting area which I do recommend. Better students should also consider mastering the scenario function within Excel. This function is quite powerful, but it does take a bit of care to master. Again, it's not necessary for the pass level. For this module, I'm not setting a specific activity exercise because the basic activities have already been covered in FinTutor in tasks 2 and 3. But what I'd expect students to do is take the opportunity to apply those tasks and build as many tables and charts as you can off the model you've created. With the insights you take from this, then apply it to your model, and you can set about getting your assignment model up and going well.